In this lab, we were to use a given video of a mass attached to a spring and analyze it in Tracker to obtain data on its motion. Using the initial conditions obtained from Tracker, we were to model the mass's movement with the computational model. We were able to predict the motion using Newton's second law and energy principle. The goal of this lab is to compare the actual motion of the mass to its predicted path and analyze the different forms of energy produced from its motion to determine whether the energy principle is satisfied. In Tracker, before the motion was traced, the spring length at rest was set to 0.7 meters, and the axes were set so that the point of attachment is at the origin, with the spring falling in the negative y direction. To use Newton's second law to model the mass's movement in the computer code, we need the net force on the mass. The net force comes from the two identified forces acting on the spring, the weight force and the spring force. The sum of these would produce the net force needed to predict the motion. The initial conditions for the code were set using the information plotted in Tracker. At time 0, we extracted the initial positions and determined that the starting velocity was 0. We know the mass of the object to be 0.402 kilograms and that the gravitational field on the Earth is 9.8 meters per second squared. Newton's second law, along with Hooke's law, is used to predict the object's motion. We used our knowledge of periods of oscillation to determine the spring constant, and with Hooke's law, the spring stiffness was found and used to determine the spring's relaxed length. We know the force of the spring to be Ks and the force of gravity to be mg. The period of oscillation is found using 2 pi square root of m over k. Rewriting it, we find the spring stiffness K can be found with 4 pi squared m over t squared. Because the weight, in this case, is moving in both the x and y directions, there are two ways to estimate the period of oscillation, one using the x coordinate points and the other using the y. The mass is constantly moving, so we take an average using 3 periods. In the x direction, we find 3 periods to be 4.748 seconds, so the average for 1 is 1.583 seconds. For the y, we found the average oscillation period to be 1.456 seconds. You get two different answers using the different coordinate values because the weight is in a different position at the different time periods. The weight is traveling at a different rate between the different axes. Using the x value period of oscillation, the spring constant is found to be 6.333 newtons per meter. We know that to find the relaxed length of the spring, we set the forces equal to each other, mg equals ks, and solve for the initial length, found to be 0.078 meters. Using the numbers we just solved for and inserting them into the code, we can model the weight's movement on the spring. The computational model, using the initial conditions from Tracker, appears to follow the same motion observed from the original video. The mass moves in a slanted circle. The computational model predicts the mass's motion with a blue ball. The model traces the weight's path to illustrate how the spring alters the weight's position. You see two forces acting on the mass at the end of the spring, represented by a blue and a black arrow. The black arrow is the force of gravity, and the blue arrow is the spring force. When we introduce the energy principle to the code, we must identify a system so that the work will be equal to 0. For the work to be 0, there needs to be no interactions, so our system has to include the Earth along with the spring and the mass. The lack of energy transfer to and from the surroundings with the system means there is a total change in energy of 0. The different energy changes are identified as the change in kinetic energy of the mass, the change in gravitational potential energy, and the change in spring potential energy. When we run the code, a graph is produced modeling all the different energy changes. If we zoom in on it, you can see the different lines better. The change in potential energy of the springs in red, the change in potential energy of the gravities in green, and the change in kinetic energies in blue. The change in potential energies, the green and the red lines, oscillate. They're roughly the same size but on opposite sides of the x-axis, which matches the movement of the mass. The yellow line models the total change in energy, tracing over the x-axis, showing that the total change in energy is 0 and therefore that the work is 0, which proves that the energy principle is satisfied in this model. So there are two ways to compare the predicted and the observed models. The first is using the VPython visual. The red ball represents the observed data and the blue the predicted. As time passes, you see that the two balls follow a similar path, with the red ball seemingly jerky at times. Time intervals at which the ball was recorded for the predicted motion were much smaller than that of the observed motion from Tracker. Another way to compare the predicted and observed models is through a graph of the y positions of each. The graph shows that the observed and predicted energy graphs follow the same general trend, but differ significantly, especially as the time increases. An explanation for this could be the fact that the drag force was not included in the predicted model, but it is in fact a very real force in the observed model.